The next property we want to talk about is distributivity. This is a common rule that we use all the time when we mix multiplication and addition for real numbers. If A, B, and C are real numbers, then A multiplied by B plus C is AB plus AC. A plus B multiplied by C on the right is equal to AC plus BC. So just like for associativity, distributivity for matrices is very easy once we know distributivity for two matrices and one vector. So we're going to take two matrices, A, whose columns are V1, V2 down to Vn, and B, whose columns are W1, W2 down to Wn. And we're going to take an n-dimensional vector U with entries U1, U2 down to Un. If we first add A and B together, then act on U on the left, that should be the same thing as AU plus BU. The proof is what we often call a definition chase. We remember that by definition, the matrix A plus B is the m by n matrix whose columns are the sum of the columns from A and B. Next, we recall the definition of multiplication of a matrix by a vector is a linear combination. So we take U1 times V1 plus W1, add that to U2 times V2 plus W2, keep going until we finally arrive at adding Un times Vn plus Wn. We remember that scaling for vectors is in fact distributive. So we can distribute, and then because addition for vectors is commutative, we can rearrange to group all of the ui, vi terms and group all of the ui, wi terms. Finally, we remember that each of these linear combinations is the definition of A multiplied by the vector u and B multiplied by the vector u. And now we're done. So for the more general case, we need to be careful about our dimensions. So in general, if we take a matrix A with columns U1, U2 down to Um, which is an L by M matrix, that is, there are M columns. Each column is an L-dimensional vector. B is a matrix with columns V1, V2 down to Vn. And C is a matrix with columns W1, W2 down to Wn, are M by N matrices. That is, each of the V's and each of the W's are M-dimensional vectors, and there are N of them. And finally, D is a matrix with columns x1, x2 down to xp. That is an N by P matrix. That is, there are P columns. Each of them are n-dimensional vectors. Then, the following products make sense. We can add the two matrices B and C together. The result will be another M by N matrix. Since A is an L by M matrix, we can multiply this on the left by A. The result of this operation will be an L by N matrix. Similarly, we can multiply the matrices A and B together, as well as A and C. Those will also give us two L by N matrices, so we can add them together, and this will be the same as A times B plus C. Now, because B plus C is an M by N matrix, and D is an N by P matrix, we can multiply B plus C on the right by D. So when we multiply the M by N matrix B plus C by the N by P matrix D, we get M by P. And just like before, we can multiply B on the right by D to get an M by P matrix. We can multiply C on the right by D to also get an M by P matrix. We can add those two matrices together to also get an M by P matrix. And these two M by P matrices are the same. And again, to give you an idea of why this should be true, we can use the previous result where our third matrix was a vector to generalize. So we start out with A multiplied by B plus C. We'll write out the matrix B plus C as V1 plus W1, V2 plus W2, down to Vn plus Wn. Next, we'll multiply this matrix by A. That means we multiply each of the columns by A. Now, in each column, we can distribute A across the sum Vi plus Wi. Next, we can recognize that by putting the AVI's together and the AWI's together, this matrix is the sum of two matrices. Finally, we use the definition for matrix multiplication to recognize each of these as A times B and A times C. For the other distribution, B plus C times D, we'll need to use the fact that when we add two matrices, then act on a vector, that's the same thing as acting on the vector with each of the matrices and adding them together. So we start out by writing D as an array of its columns x1, x2, down to xp. Next, we use the definition of matrix multiplication. B plus C is a matrix, so B plus C times D can be expressed as the matrix with columns B plus C times x1, B plus C times x2, down to B plus C times xp. Now, for each I, we can use the fact that B plus C times xi is the same as B times xi plus C times xi. We can recognize that each of these columns arise as the sum of the matrix with entries bx1, bx2, down to bxp, and the matrix with columns cx1, cx2, down to cxp. Finally, we recognize the first matrix as B multiplied by D, and the second matrix as C multiplied by D. And there you have it. That is the two types of distributivity for matrices. So we have A plus B multiplied by C is equal to AB plus AC. B plus C times D is BD plus CD, as long as the dimensions make sense